So you may remember that pedigrees are charts of family histories which show the phenotypes and family relationships of the individuals using symbols to represent different family members. You should remember that squares represent males, circles represent females, filled-in symbols represent individuals which have a genetic condition, and a proband is the first affected family member that seeks medical attention. Now we're going to start using these pedigrees to determine what kind of inheritance pattern a particular trait has. Let's imagine we're geneticists studying pedigrees to determine the type of inheritance in a rare genetic cancer syndrome called Peutz-Jeghers syndrome. We'll call Peutz-Jeghers syndrome PJS for short. If this is the pedigree for a family with a history of PJS, what do you think this inheritance pattern means? First, do you think that this is a dominant condition, a recessive condition, or neither? If you said that this is a dominant condition, you're right. Notice how PJS is passed along directly from an affected parent to some of their children, and that only the affected children can pass PJS along to their own children. Dominant conditions rarely skip generations, which makes them easy to follow through a pedigree. Now, there are some exceptions to this rule, but that's another topic for another day. Okay, we've determined that PJS is a dominant condition. Now, do you think that PJS is autosomal or sex-linked? You may remember that autosomal means that the causative gene is located on an autosome, and sex-linked means that the causative gene is located on the X chromosome. If you said that PJS is autosomal, you're correct. Here's why. If the causative gene was located on the X chromosome, then a father could not pass PJS to any of his sons, because sons inherit a Y chromosome from their father and an X chromosome from their mother. Also, since daughters inherit an X chromosome from their father, we would expect all daughters of an affected father to also have PJS if this was a sex-linked condition. In this case, the proband's father has passed PJS along to some of his sons and some of his daughters, so this must be an autosomal condition. On average, an autosomal dominant condition is passed from an affected parent to about half of their children. However, be careful not to read too much into the exact ratio within a family. Each child of an affected parent has a 50-50 chance of inheriting the causative allele. It's pretty much a coin flip for each child. It is entirely possible for a person with an autosomal dominant condition to have several children who do not receive the dominant allele, and are therefore all unaffected, just like it is possible to flip a coin 5 times and get heads every time. Now let's look at the pedigree from a different type of genetic disorder and see if we can determine the type of inheritance again. This time, we're looking at an example of what a pedigree might look like for a rare genetic disorder called galactosemia, which is a metabolic disorder where the person cannot properly metabolize galactose. What type of inheritance does this disorder have? Do you think it's dominant, recessive, or neither? In this case, it appears to be recessive, but we can't be completely sure that it isn't some type of more complex inheritance. In a recessive condition, it takes 2 copies of the affected allele to cause the condition, one inherited from the mother and one inherited from the father. So most individuals that inherit an autosomal recessive disorder have unaffected parents. However, both of these unaffected parents should each have 1 copy of the recessive allele, which would make them carriers of galactosemia. A carrier is an individual that has 1 copy of a recessive allele and does not exhibit the trait. In a pedigree, carriers can be designated by placing a spot in the open circle or square. Some carriers of a disease are inferred by relationships to affected individuals, but with advances in our knowledge of human genetics, it's now sometimes possible to do genetic testing on individuals and determine if they carry the recessive allele or not. Because both of our proband's parents are carriers for galactosemia, each of her siblings has a 1 in 4 chance of also inheriting the condition, and a 1 in 2 chance of inheriting 1 copy and also being a carrier. As a result, nephews and nieces of the proband may inherit galactosemia if the proband siblings has kids with another person who also happens to be a carrier. Now, do you think that galactosemia is autosomal or sex-linked? If you said autosomal, you're correct. Sex-linked conditions generally affect males because they only have one copy of the X chromosome, and therefore only have to inherit one copy of the causative allele, while females have to inherit two copies of the causative allele. In this pedigree, we have one male and two females that have galactosemia, so this is an autosomal condition. Autosomal recessive conditions are difficult to identify from pedigrees alone because the condition often skips more than one generation. In addition, affected individuals have to inherit copies of the recessive genes from both parents, and even if both parents are carriers, only one out of every 4 of their children are likely to be affected. However, sometimes autosomal recessive disorders can be identified from pedigrees alone if the pedigree is very large. In families where parents have lots of children, say 8 or more, the 1 in 4 ratio of inheritance of an autosomal recessive condition from 2 carrier parents might become more identifiable. In addition, a long family history also increases the chances of identifying a rare autosomal recessive condition that makes an appearance in a family every few generations. Now, what type of inheritance pattern do you think we see in this pedigree? If you said sex-linked, then congratulations. You're either good at analyzing pedigrees, or you're good at using the process of elimination. Sex-linked conditions, like hemophilia A, are caused by recessive alleles on the X chromosome. Hemophilia A only affects females if they inherit 2 copies of the causative allele. However, since males only have one X chromosome, only one copy of the allele is needed to make them hemophilic. Much like autosomal dominant traits, sex-linked traits also have very recognizable inheritance patterns. Sex-linked inheritance often follows a crisscross pattern of inheritance, where affected males pass a sex-linked recessive gene to their daughters, who become unaffected carriers of the trait. These carrier females then pass the affected allele to half of their sons and daughters. The sons that get the affected allele exhibit the trait, while the daughters all appear to be normal, even though half of them are also carriers. Affected males always pass the causative allele to their daughters, but cannot pass it to their sons. The inheritance pattern is described as crisscross because the trait almost always appears in males who inherit the allele from their mother. In addition, in the few cases where a female does have a sex-linked disorder like hemophilia A, her father and all of her sons will also have hemophilia A. Notice that in this pedigree, the proband's father and sons are all hemophiliacs. However, her mother and her daughters are not affected, but all of them should be carriers. Going back to our original pedigree, the children of a hemophiliac father would in most cases all be unaffected. However, all of his daughters would be carriers, and on average, half of their male children will be hemophiliacs. In contrast, no children of the affected father's sons can be hemophiliacs, unless one of the sons happens to have children with a carrier female. Notice how sex-linked traits skip generations, affect mostly males, and cannot be passed from father to son. One last word of caution when analyzing pedigrees. Although different types of inheritance have some recognizable inheritance patterns, there are lots of variations that are possible with any type of inheritance. Because of this, it is important to analyze pedigrees carefully and think critically about how the alleles for a trait are being inherited by each family member. For example, we just talked about how a father cannot pass a sex-linked trait to his son. However, it is possible for a father and son to both have the same sex-linked trait if the mother of the son is a carrier. Let's review. Autosomal dominant conditions